All right, how's it going, everybody? We are here on Tuesday of week 7. This is our one lecture video associated with this week because we're having our test this week as well, so we're only going to cover half as much stuff. I'm assuming that a vast majority of you aren't going to see this video until after the test is done, but if you're watching this beforehand, our test will be from noon on Wednesday until noon on Friday. It will be available on Canvas starting at noon on Wednesday. You'll all go work on the test on your own and submit to me one single PDF in Canvas by noon on Friday. So that will be available there to be done this week. So today we're just going to talk about approximate integration as our one topic for the week here, and then we'll look at our last topic. As you can see, next week we'll start with some Chapter 8 stuff right there. Section 7.8 is going to be a relatively easy section here for us of indefinite integrals, introducing infinities into our upper and lower bounds. And that really won't be too difficult to manage, but it's going to be really important for our upcoming topics in Chapter 11 at the end of the semester here. So we'll pick up with that on next Monday. So today's topic is approximate integration. This is like a weirder section than like most of the other stuff that we talk about here, because sort of the whole point of today is us saying what happens when we can't do calculus. So this is like different than other calculus topics because this is specifically what do you do when calculus fails you. As I said, you're going to see a lot of words on the screen today. Part of the reason why I had to not do this video yesterday and do this today was because I've just been having these weird issues where my keyboard and mouse like just stop responding for between 20 seconds and 20 minutes at a time. And yesterday I had a huge amount of typing to do to get all of my things up on screen, and I managed to get my stats stuff ready for yesterday, and my keyboard was just giving me hell, and I could not get my things typed out. You're going to see there's a pretty notationally heavy section here. And so since we only had one video lecture, I was like, I'm not going to stress out over being angry at my computer, and I'll just bump this over to today now. So I now have this all typed out here. So what you're going to see is that this section here involves a huge amount of doing small, simple computations, tons of multiplication and addition. You will greatly benefit from figuring out ways to do this smartly using technology. TI calculator, Excel is honestly probably a pretty smart thing for you to do here to figure that stuff out. I'm going to show you some Python code that I've written, and I'll also show you how you can install Python on your own computer and just take the code that I've written and lightly modify it for your own purposes. So I'll talk about that when we get to it, and I'll post the Python notebook that I have created in Canvas in case any of you want that. If any of you at any point want any help setting up Python things on your own computer, that's one of my favorite things to do is to get people programming. So I would love if you would say, hey, Tony, can you help me get Python set up so I can look at the notebook that you made? That would make me so happy. So why do we care to talk about approximate integration? It's annoying to do, so we should have a good reason why we care to do it. There's two huge reasons that are pretty important. One, we've been talking about the fact that most functions are not directly integrable. We can't find an integral for the integral of e to the x squared, a really important one that we talked about. We're going to see more things about e to the negative x squared when we do our probability section in Chapter 8. So if you were to just randomly select one function from the wide universe, there's about a 0% chance that it's actually truly integrable. And so it matters that functions that we cannot find an antiderivative for, that we still have some way to make estimates of the area that is underneath the curve. The other reason is because in lots of application settings, data is collected, but we can't quite find a curve that necessarily fits that data close enough to make it reasonable to use a curve instead of the data itself. For example, if your car keeps a record of what your velocity is every 20 seconds, that should be very useful in us helping figure out the total distance that you've traveled, but it might not be the case that we can come up with a curve that perfectly fits through whatever all those data points are going to be. We still are interested in being able to do the concept of integration, but rather than actually having a function to find an antiderivative of, we really just have a table of values to use as our outputs to understand things, and still getting the concept of there being X values and Y values and us being able to determine heights underneath certain places, stuff like that. So these are two huge things that happen all the time. Most functions aren't integrable, and most data doesn't have a function that fits it. But that doesn't mean we don't want to still think conceptually about the idea of integration behind those ideas. We just need to approximate our integration, since we either can't find an antiderivative, or don't have a function to find an antiderivative of. So very, very common that approximate integration comes up in absolutely tons of real world applications. This stuff matters here. Ultimately, at the end of the day, these approximation techniques are pretty much never truly performed by hand by anybody. You're going to do a couple of these kind of by hand, but honestly, like I said, I'm hopeful that you figure out ways to make these happen in your calculator in Excel. I am going to expect you to be able to write a few of these out when we take our next test. I am going to say show work for doing this approximation right here. It's not going to kill you. This is one of those things where it's annoying, and you need to experience the aggravation of it so that you understand the value in using technology. You won't really realize how nice it is that technology does this for you until you have to do it by hand, and that's why I'm going to make you do that. Now that you are reaching mathematical adulthood, you should also realize that no estimate of anything is meaningful if we don't have a way to measure the goodness of that estimate. Therefore, error analysis is something that should always be a part of every approximation technique that you ever discuss for the rest of your mathematical life. It doesn't matter if you can come up with an approximation for a value if you can't tell me how good that approximation is going to be. Right? So error analysis, analyzing how much error we have in our approximations, is always a partner of performing approximations, is understanding how accurate those approximations are going to be. That, to me, is the actual more interesting part of this unit, this section, because everything else in this section is just a bunch of fancy multiplication and addition, so it's not that exciting. Right? The good news is that understanding all of these approximating techniques that are going to happen in this section is pretty easy. So we're really going to talk about them conceptually. I'm going to go so far as to literally not actually do one single approximation in this video lecture here. I think that you guys can do them. I want you to understand why they are constructed the way that they are, and to recognize the parts of them and why they're there. All right, and we've already even done several of these. There are 5 total approximations that are covered in this section. We've seen 2 of them, we skipped 1 of them, and 2 of them are new. Left hand and right hand Riemann approximations are things that you saw back in Calc 1 that we vaguely, briefly revisited in week 1 of our semester, this semester. The midpoint rule, I believe that I skipped this section. I think that this is in section 5.5 or something in our textbook, and I skipped it because I knew that we were going to discuss it out here in this section. Trapezoid rule is new to us, but it's very closely related to the midpoint rule. There's nothing fancy really going on too much with the trapezoid rule, but it's better than our number 1 and number 2 approximations here. Simpson's rule is the one that's different than the rest. It's the one that's going to take us a little bit of effort to figure out what's going on. There is actually calculus that happens associated with the derivation for Simpson's rule, whereas there's no calculus that happens in 1 through 4 here. So it's a little bit more exciting, and it's better than the rest. And so we really want to understand Simpson's rule maybe more than the other ones here. And it's the one that sort of takes the most effort to understand, but I still don't think it's that difficult right here. So what we're going to do is we're going to cruise through the 4 easy ones right there. And then, like I said, we're going to cruise through the 4 easy ones. I'm not even going to directly do any examples of doing any approximations with them. Then we'll stop and we'll much more carefully look at where Simpson's rule comes from and actually derive its formula. Then we'll come back at the end and we will looking at error analysis for our 3 good estimates. We're going to see here that our left and right hand Riemann approximations are noticeably less good than these 3 here, and so we're not even going to talk about error analysis for these 2, but we'll talk at the end of error analysis for these 3. And the only example that I'm going to do today will be the error analysis associated with a Simpson's rule approximation. So let's go ahead and do this. This is going to be one of those ones where if you're watching this video, by the way, after the fact, if you're watching this as a recorded video right now on the YouTube video through Canvas, I would recommend that you stop right now and snag the PDF of this lecture. This is one of those things where I did my fist shaking at you guys, and I'm like, you should not just read the lecture documents. I'm going to say a lot of important words. You need to watch the video instead of just reading the PDFs that I make. This is one of those ones where it's going to be way easier for you to do things if you have the PDF kind of like open with you at the same time. Otherwise, if you're watching along with me right here live, maybe get your textbook out, or just realize that you're not going to be able to take notes fast enough to keep up with the pace of this video, because there's just a lot of notation that happens here. But it's okay. It's nothing too crazy. So let's go ahead and kind of walk through our first four simpler approximations here. So first things first, the left-hand rule. This is the first Riemann sum that you ever did. If you use the Stewart textbook, then this is the first approximation. It's first a left sum and then a right sum. We can see I've got our little diagram here of our left sums, our right sums, and our midpoint sums. We'll see the same diagram two more times for this next two rules right here. To estimate the value of a definite integral, we subdivide the interval, x is an element of the interval from a to b, into n subintervals. We determine the areas of the rectangles whose left corners touch the curve. That's why this is the left-hand rule. And we should notice that since we're using the left corners, as you can see in this diagram, this amounts to using, notice here that there are 5 x values of interest here on the x-axis, 5 bounding x values, but only 4 corners are used to cover that. The fifth one in the left-hand rule is the unused one. The last one is the one that is discluded. All but the last x value in our list of x values of interest are used to make our approximating rectangles associated with this approximation. So what does this look like? Well, in our left-hand approximation, by the way, this is something that I wrote out in the first couple of them and then I stopped writing. It's always going to be the case that we need to compute a delta x, the width of a given subinterval. We're going to have rectangles for all 5 rules here. Or, okay, the bottom of our geometric shape is going to be a rectangle in all 5 of our rules here. So we're always interested in the width of a subinterval. That's always going to be delta x. It's always going to be b minus a over n. The total width of the interval of interest divided by the number of subintervals will give us that. So I'm not going to talk about delta x ever again today. That's always the same. Delta x, b minus a over n, never changes. In this case here, we form our list of x values that are of interest to us, as our first x value is always a. That is our lower bound point that we're looking at right there. To get to our next x value, we start from a and we add on one single delta x, one width. That's what we call x1. Add 2 delta x's to a to get x2. We do this out to the end, but notice that because we never actually get to b, we always only go up to n minus 1 delta x's being added on to a. And notice that this x list right here is one way to notate this. More typically, we notate this more casually as x sub 0 up through x sub n minus 1. Since we start at 0 and go up to n minus 1, there are n objects in this list. It's the n subinterval locations. The left side of the n subintervals are accounted for in this x list. To estimate our area, we know that we just want to add up a bunch of rectangle areas. So this is the width of a rectangle, delta x, times the height of the rectangle, with the left-hand corner being the height determiner right there. So this is width times length of the first, plus width times length of the second, all the way up to width times length of the last. And again, it ends at n minus 1 because we never use x sub n. That would be a right-hand corner. So we'll see x sub n in our next sum. We simplify this a little bit by noticing that delta x is just a constant, so we can factor it out of everything here. So here I've factored out delta x, and then this is really just a sum of the heights. And what I do, leave off my last parenthesis right here. I need a parenthesis, Captain. So we factored out the constant delta x. Delta x never changed across all of these, so delta x got factored out. This really then should just be the common width times the sum of the heights, and we rewrite this into our more compact summation notation, which, by the way, Microsoft Word's equation editor has gotten a lot better in the last when I started teaching 7 years ago, it was a real pain to use the Microsoft Word equation editor. It's much nicer now. It still really bothers me that it refuses to do the above and belows on the inline sums right here. So I wrote this out slightly more nicely. We then refer to this as the left-hand sum broken down into n subintervals is going to be equal to the common width of all the subintervals that we factored out times the sum of the heights of all of the x's. Notice here, very importantly for notational purposes, that my bounds of summation changed a little bit right here. Notice this is by far the hardest part of this whole section is tracking notation. So I want to be really clear about what happened notationally here. In this sum, we were suggesting that our index I was going to start at 0 because our first subscript was 0. we wanted to go up to a final subscript of n minus 1. And so we gave our upper bound as n minus 1. And we said that all of the subscripts on x will be these I values. So I began at 0 and I went up to n minus 1. That perfectly agrees with what we have written on the line above. But I wrote it down here different. Right? Notice that I changed this I right there within the sum, our index on the x. I changed this I to I minus 1. So all of these should be one fewer than they were before. But I bumped up the bounds by 1 to cancel out with that. So I reduced the index inside the sum by 1, but I increased the index boundaries outside of the sum by 1. And those two changes, in a sense, cancel out. You should notice here, this starts at I equals 0 and goes up to I equals n minus 1. Here, when I plug in my first I value of 1, we get x sub 1 minus 1. That's x sub 0. It will go up to the I value. The last value we use for I is n. But when you plug it in down here, that's going to give you x sub n minus 1, which does perfectly match this guy up here. So I did do a little bit of a change of my bounds of summation here. The reason why we want to do this typically is because I really want the structure of this sum to perfectly match the structure of our upcoming right-hand sum so that we can compare them more directly. Our right-hand sum more naturally looks like this. So it's just a typical thing to do to adjust some bounds of summation here. So take a moment if you're not convinced, if you're not handy with your sums yet, to convince yourself that these two are going to give us the exact same list of x sub I values right here. So which one is better? So Coffee Gopher's question here is, so which index is better to start with? There's a definitive answer, right? And he's saying, should we be starting with I equals 0 or should we be starting with I equals 1? What I would say is, I think that consistency matters more than which one. And so what I would say is, especially in this case today that we're comparing a series of 5 different summations, we want all of our summations to be structured the same. So I would say here it sort of doesn't matter, but if we kept on interchanging between zeros and ones, it gets kind of confusing to compare between the two of them. So I would say, and what we're going to see also, by the way, is we're going to see, Coffee Gopher, I think the answer to your question is going to be better answered out in chapter 11. In chapter 11, we're going to deal a ton with sums, and we're going to see cases where it's preferable for us to take a sum that starts with a bound of 0 and rewrite it as a bound that starts at 1, with the 0 term picked off as an individual term so that we can manipulate sums. And again, it's because we're going to want to use these sums in comparison with other sums. So I would say that your answer is there's generally not a truly favored thing. I think in general in life, you always want to do math with 0 and 1. Those are our favorite two numbers. But it matters more that when we are comparing sums or trying to do math with multiple sums, that we try and just standardize it, get them all to have the same bounds so that we can then do math between sums more sensibly. So this is more of a consistency thing than a 0 is better than 1 type thing right here. Because, and I should say, what we totally could have done, what we're doing right here is we're trying to make our left-hand sum notation match our right-hand sum's notation, but that's an arbitrary choice. We could have chosen to leave this left-hand sum like it was written right here, and then make our right-hand sum match this one instead, and we could have done that either. I'm just matching the book's notation right here. So it's more about having equivalent notation across each of the sums that we want to compare is more important. Very good question. But again, if you're not convinced with this, I would recommend that you just like lightly play around with this a little bit right here. And maybe what I would just say is like, in fact, let's just write this out once so that everybody's convinced. Because I know that some people are totally down with it and some are not. Notice here that if I do I equals 0 to 5 of I, then this would be 0 plus 1 plus 2 plus 3 plus 4 plus 5. Right? That's the sum from I equals 0 to 5. On the other hand, I could set this up as like I equals 3 to 8, but have my sum be the value is I minus 3. Well, here I'm going to use my first I value as 3, so 3 goes in here. 3 minus 3 is 0. Yeah, it's easier for some people. Good one. You know, puns will get you banned in half the channels on Twitch here. You're lucky. I'm not going to do that right now. But here we're still going to get the same exact thing here, right? So this is saying you can make adjustments to the bounds on the outside, and if you make the opposite adjustment on the bounds on the inside, then those adjustments should effectively cancel out right there, right? So this is two different ways to write this same exact sum right there. I think that this second one here is objectively worse. than this first one right here, but zeros and ones are very commonly the most common starting boundaries on lots of sums that are out there. But we will see in chapter 11 a couple that sort of meaningfully start at like 2 for a good reason, and we'll have a good reason to do so. Okay, so there's our first one, and like I said, we did Riemann sums. Technically, this is Calc 1 right here. It's just part of this unit, so we're talking about it. So I'm going to go through the right-hand rule even faster. This is the second Riemann sum you ever did. We're going to take this same integral. We're going to subdivide it still into n subintervals. We're now going to determine the areas of the rectangles whose right corners, upper right corners, touch our curve of interest. This is equivalent to using all but the first x values. Before we discluded the last, now we're discluding the first. You should notice in our diagram right here that our x value of a is not one of our corners of interest right there. Our first corner of interest would be officially the second x value in the list, and we do use the final x value of interest as one of our right-hand corners right there. So this first one, the left-hand rule, does use a and it doesn't use b. The right-hand rule doesn't use a, but it does use b. And we'll see the midpoint rule doesn't technically use a or b, but we're going to need all of our parts in there. So nothing super special here. As with before, delta x defined the same way. X list before our first term was just a. Now our first term is a plus delta x to get to the right edge of our first bar. We do go all the way up to b. This is b right there. A plus n times delta x. We've done a chunks further than x. This is equal to b right there. A is not included in this list. So here our x list, before our x list went from x sub 0 to x sub n minus 1, that was n objects. Now we're instead starting at x sub 1 and going up to x sub n, that's n objects. Our area estimate in this case, right here, is going to be formed exactly the same way, right? The only thing is a little different subscripts right here. Delta x is a constant, factor out the delta x. We're left with the sum of heights from x sub 1 to x sub n, remembering that x sub 0 is really the true first one, that's a. And again, we're going to write our sum right here, and notice here we again have this I equals 1 to n of f of x sub I. So if we start with I equals 1, our first height is f of x sub 1. And notice again, this one we didn't make any adjustment to our boundary, because when we did our left-hand sum, we changed it to just match what we were going to get for our right-hand sum right here. But we could have done it the other way. We could have just written this kind of backwards the other direction right there. And in fact, maybe we should just do this right here. We could write this as being delta x times the sum of. I could instead do this as f of x sub I plus 1 and go from I equals 0 to n could be a thing I could do, because now we'd start with I being 0. And if I is 0, then the first term we're going to get is really associated with x sub 1, because 0 plus 1 is going to give us 1 down there for the subscript. So this would be relating it back into the opposite context of starting with the I equals 0, or we could do the I equals 1. It doesn't matter. They're equivalent to the same thing right there. We got to decide for ourselves which one's more sensible for us to interpret. I guess I kind of like and I guess they go either way though. The minus 1 in the left sum helps remind me that we want all the left numbers and disclude the rightmost one. Maybe this plus 1 helps remind me that we want the rightmost numbers and not then ditch off a, that we skip the first one or something like that. I don't know. They're equivalent to each other right here. We'll get better and better with sums here for sure this semester. So these two aren't exciting. You've literally done all this before. Nothing new there. Midpoint rule. First thing that's new to us here. We skipped this one officially back in chapter 5, but I skipped it because I knew we were going to talk about it right here. We're going to do basically the same exact thing here as we did with our left and right sums, but instead we're going to take all of the x values, right? So in the left sums we use a and we disclude b. In the right sums we use b, but we disclude a. In this case, as you're seeing at the bottom of the screen, I want to track all of my x values, because what we're going to want to use as the x ones, hey Praetorian, how's it going? I want to use all of my x values because the heights of interest are going to be defined as the average height between each of our x points of interest here, all right? So this never changes. Delta x is still b minus a over n. All endpoints, you should notice, goes from a all the way out to b. All of them are included in our list of interest here. All x endpoints, x sub 0 to x sub n. What we want to use for the midpoint rule is the averages of the adjacent pairs of these, all right? So these x bars, a bar over the top of something, for all you stats people out there, a bar always indicates an average value. So we're going to call x1 bar, we're going to define that to be the average of x0 and of x1. That's what we'll call x1 bar. So x sub I bar is the average x location of x sub I and x sub I minus 1. And I've got that statement written right here. This is the average of x sub I and x sub I minus 1. Average, add them both together and divide by 2 right there, right? So just a little bit of extra notation here. There's nothing super weird going on here. This just says, instead of picking all the x subdivision breakdowns, pick every value that's actually halfway between all the subdivision breakdowns. So we can do the average of x0 and x1, the average of x1 and x2, the average of x2 and x3, and that's what we're getting for our x values for our midpoint rule here. After that, nothing else is different. We're going to add up a bunch of areas of a bunch of rectangles right there. There's all their widths and their heights. The height is the function evaluated at each of the midpoint x values right there. That delta x, yeah, what am I dropping all these outside parentheses for right here? Shame on me. Again, that constant value delta x never changes, so we can factor it out. And now we're just adding up a bunch of function heights that are heights at each of our midpoint locations right there. So we'll describe our midpoint sum as m sub n. It's doing the midpoint rule with n subdivisions. That's m sub n. We have factored out all of the constant delta x's, and here again, we're just adding up the sum of all of our heights at our midpoint locations that are right there. Here, I'm just saying to define the midpoint rule. I feel like you got to kind of explicitly say what you mean by yeah, m sub n as the x bar right there. I feel like it could be interpreted that x bar would go the other way, that it's the average of the current location and the next one. So we just want to be explicit that here we define the x bar as the x value in the previous one. Technically, we could have set this up slightly differently, and we could have stated a different summation for it. This is the way that this is typically defined. That's right here. And so here's our statement for the midpoint rule. You should recognize that this is nothing distinct from what we're doing with our left and our right hand sums out there. This is really just doing basically the same exact stuff right there as we were doing before. We have just computed where our x values are going to be slightly differently right here. Doing that, we basically have our third sum. And again, you should realize that all this really is right here is us just doing more left and right sums. This is just a Riemann sum, but the only difference is that we've taken halfway between for our x values, right? So for the trapezoid rule, for our trapezoid rule over here, we are going to do something super duper similar to the midpoint rule. And you should notice our diagram has finally changed over here that we've been looking at. In the midpoint rule, what we did is we averaged adjacent x values. Right? Then we summed the area of the associated rectangles. In the trapezoid rule, we are going to sum the rectangles with trapezoidal tops. Technically, this shape is a trapezoid, but I typically think of there not being a perpendicular part down there, but this is still technically a trapezoid right here. So I just call this a rectangle with a trapezoidal top, right? It's going to have the skew top right there. What we want to see is that just like in the midpoint rule, we were averaging adjacent x values. In the trapezoidal rule, I'm going to just draw a quick, simple picture right here, and we're going to see that this is more like taking the average of adjacent y values here. So it's going to be a very similar conceptual thing. So here's the picture that you should see here. If I'm going to draw one rectangle with a trapezoidal top, then what you should see is this is the average of using the lower height as our rectangle plus the upper height as our rectangle. Height divided by 2, right? So notice here that if we were to, so I guess I'll just put my dotted line box right there. If we average these two heights, then what we're going to get is a height that's passing right through there. And you should notice with my little dashed line there, the missing height, the error right there, is equal to the extra height that we're getting in the piece that's right there. So we can average two just straight up rectangles, and that will give us the area of one trapezoidal piece that's right there, right? So a trapezoid with a rectangular base has an area that is equal to the bottom bound rectangle averaged with the upper bound rectangle right there. So midpoint rule says average adjacent x values. trapezoid rule says average y values right there. That's our conceptual relationship between our midpoint and our trapezoid rule here. So our notation will be a little bit hairier for this one, but not really too bad, right? So first things first, we collect all of our x endpoints. Notice that this is n plus 1 endpoints right here, 0 through n. That's all of our endpoints that give us the n subdivisions. The area of our first trapezoid then, the very first one, it's going to have a width of delta x, like everything does, but the height of it is going to be the average of the first x value's height and the second x value's height, right there, right? That's exactly what our computation is over here. This is my x sub 0. I'm clicked on something, so it's unhappy. There we go. This is my x sub 0. This is my x sub 1. This is my, right here, this is f of x sub 0. And this height right here is f of x sub 1. If we average f of x sub 0 and f of x sub 1, we will get the average height of this guy right here. We can multiply the average height by the width, and that's an area of a trapezoid right there. So that's the area of our first trapezoid. We just want to add them all up now. We've just got a whole bunch of those pieces. The very interesting thing for you to notice is that f of x sub 0 is the first height in our left-hand sum. F of x sub 1 is the first height in our right-hand sum. It seems like what we're going to do if we add up a bunch of these chunks is just find the average of our left-hand sum heights and our right-hand sum heights. And that's actually exactly how this is going to pan out for us here. So it looks like what we can do is our trapezoid sum is just literally the average of our left-hand sum and our right-hand sum from our Riemann sums right there, which is very convenient for us here. So our area estimate then, this is just my average. This is my left-hand sum as my first piece. This is my right-hand sums area as my second piece. I added them together and I divided by 2. I have found the average area of the left-hand and the right-hand sums, and that is going to be equivalent to our trapezoid area here. Notice, I think a good thing to notice here as far as what individual terms do you get if you're doing these by hand, you should notice that our left-hand sum does include a as a height, but our right-hand sum doesn't. So we're only going to get one copy of the a height. Our right-hand sum does have b as a height, but it doesn't have a. So we're only going to get one copy of b from our final height from the right-hand sum. All other heights are common to both the left and the right-hand sum, so we're going to get 2 copies of all of those guys in the middle. So 1 copy of the height at A, 1 copy of the height at B, 2 copies of all the heights between A and B get added up. And because we're averaging, we divide by 2. The delta x is the width that's associated with this. So this is width times the average height is going to give us our total area estimate right here. And so notice we get this real nice little statement here for our trapezoid area right there. So if you're doing this by hand, it's going to be less work for you to do this in the written out way right here. But if you're doing this like computationally, if you have technology to help you, it might be easier for you to just compute the left and the right sums and then just average them to get your trapezoid sum that's out there. So there's our first 4 sums right there. Hey, look at that. Only 35 minutes for me to talk about our first 4 sums with all this crazy notation going on out here. And again, by the way, I'm going to come back to Coffee Gopher's question. Now notice, we have now built an equation that involves 2 sums in it. It is incredibly valuable for us to have matching boundaries on these sums, or else you are going to make mistakes, right? It's just like, this is really more of a consistency thing. Don't add together a bunch of summations that have different bounds on them, because then it's really difficult to tell what pieces we should be getting out of them right there. So consistent bounds are very good for us right here. So our trapezoid rule, very easy. The trapezoid approximation is the average of the left and right hand approximations. Cool. So we just knocked out 4 of these real quick. I didn't do any examples, but like I am sure that you can do multiplication and addition carefully. So I think you're good. So there are the first 4 out of the 5 sums to discuss. We still need to talk error bounds. Left and right hand sums are so boring, we're not going to talk about error bounds for them, but we will come back and hit our error boundaries for our midpoint and our trapezoid rule. Hopefully what your takeaway so far is, we're just doing a bunch of super basic geometry. There's no new concepts happening here beyond what you already knew about left and right hand Riemann sums. We're just either picking our x values differently or picking our y values differently. But the broad concept is add up a bunch of vertical shapes that all have identical widths. We wanted our shapes to still be easy, so we still picked rectangles. Trapezoids are like barely harder than a rectangle. A trapezoid's area is just the average of two rectangle areas. It's barely harder. By far, the hardest part of all of this is just keeping track of your notation, by far, which is why I'm not sitting here doing examples, because tracking notation is something that is sort of, I sort of think of that as more of an interpersonal lesson that you need to learn by making some notational mistakes and then yelling at yourself and then getting it right the next time. And I'm sure that you will do that in the homework here. Simpson's rule, a little bit more exciting because we're going to finally stop being in a purely geometric setting. So we're going to look a little bit more carefully at Simpson's rule. So let's do Simpson's rule approximation for our integral, and then we'll look at the error bounds that are associated with our three more exciting sums. Midpoints with n subdivisions, trapezoid with n subdivisions, Simpson's rule with n subdivisions. So here's our big concept for Simpson's rule. In Simpson's rule, okay, in the trapezoid rule, we essentially, what we did is we decomposed a curvy function into a bunch of straight line approximations, right? Straight line approximation for one subinterval, straight line approximation for the next one. We kept on having straight line pieces that defined what our curve was doing out there, rather than having a smooth curve go through them. By the way, this is what I saw a bunch of you guys did for your bowling pin problem. You guys literally figured out the trapezoid rule on your own for the bowling pin problem. You should feel pretty good about that. So we sort of decomposed our curve into a bunch of chunks that we then made a linear approximation to the curve over that chunk by really just saying beginning endpoint, ending endpoint, draw a straight line between them, find the function of that curve, find the area underneath it right there. What we really did then is we made a bunch of linear approximations to subintervals of our curve, linear approximations, first order approximations to our curve. If we want to make a better approximation, then we can upgrade the degree of our approximation. So Simpson's rule is sort of the second degree analog of our first degree trapezoid rule. The trapezoid rule says find linear pieces that represent our curve and add them up. The Simpson's rule is going to say find quadratic pieces individually over an interval. A little quadratic estimate, a little quadratic estimate, a little quadratic estimate. And we're going to stick together a bunch of quadratic approximations of our curve together, find the area underneath those. So we did our trapezoid rule, gave us a first order approximation. It gave us linear tops to all of our shapes. And we know that it takes 2 points to make a straight line. In Simpson's rule, this is now a second order approximation because we're going to come up with parabolic pieces. Second order stuff is quadratic. And what we know is quadratics take 3 points to make a parabola. So one of the big distinctions with Simpson's rule is that rather than needing to just know your beginning endpoint and your ending endpoint, like we averaged x1 and x2, we're now going to need to work with 3 x values per estimate, per little piece of Riemann information right there. Instead of 2 x values defining one piece of Riemann x information, we're going to need 3 because we're going to need to form a parabola that goes through them. So you should see in our picture right here, Riemann sums, I need 2 x bounds. Trapezoids, I need 2 x bounds. Simpson's rule, I'm going to need 3 x values so that these 3 heights, we can fit a parabolic curve through those 3 points right there. Once we have a parabolic curve fit through 3 points, then we can compute the integral of this parabola, find the area underneath, and add up all of those chunks. So you should notice in Simpson's rule, we're finally going to actually do some calculus today, because I can find this area without calculus. I can find this area without calculus. I cannot find this area without calculus. So we will find the individual areas that we're adding up for all of our Riemann parts by doing an integral. But we're going to be really smart about this, and we're going to do one integral at the very beginning, and then we're never going to do the integration ever again, because it's always just going to be the integral of a parabola every single time. So here's the fun part of today, all right? And by the way, before we move on here, notice, because we need 3 x values here for each of our groupings, there's going to be one little extra restriction that goes with Simpson's rule. It's nothing major, but it's something that we got to remember here. We want to derive the formula for Simpson's rule. How do we get this summation? We're not just following the carbon copy steps of our old Riemann sums. The limitation that you should notice is to find our parabolic chunks. For example, we're going to start and use x0, x1, x2, and we're going to fit a curve through f of x, or through the points that are associated with those three x values right there. The next adjacent set of 3 points then is going to pick right back up where the old one left off at x2. So it's now going to need 3 points starting at x2. x2, x3, x4 is the next grouping. Then x4, x5, x6 is the next grouping out there to get our 3 different chunks that we have a parabola being the top of those 3 chunks right there. What you should notice is that all 3 of these groupings end with an even subscript right there. What that is going to basically say to us is that Simpson's rule requires you to always have an even number of subdivisions. You can't do like n equals 9 and sensibly do Simpson's rule here, because you're going to end up with the last 2 chunks where you only have 2 points, and we cannot define a parabola with only 2 points out there. Yeah, so basically the deal here is that we did geometry to find 1 in our Riemann sums, and then we added them up. No calculus happened. Here we use geometry for the midpoint rule and for the trapezoid rule, and then we added them all up. But the point is, for Simpson's rule, to find one Riemann object's area, I can't just do geometry to find this Simpson's rule area. So we're going to have to do an integral to find this piece of area and add up lots of little integrals of our individual Riemann sticks. But to be smart, we're going to do one general. No, you're good, man. And again, I appreciate the questions for sure. So again, I could do only geometry with our first 4 rules and get away with it. But because we're going to use parabolic tops of our estimating pieces instead of skew straight lines or horizontal straight lines, exactly. And so pardon Reed, what you're saying is also exactly correct. Integrating a parabola is going to be a piece of cake, right? We're integrating a polynomial. This is an approximation to some maybe insane function that we couldn't otherwise integrate, right? So, yeah, and exactly. And the higher degree polynomial we use, the more and more appropriate, like graphically correct it should be relative to the thing. So what you guys should also realize is that there could conceivably be something above Simpson's rule. Maybe a 3rd degree approximation that's going to be even better. A 4th degree approximation is going to be even better. But the math is going to get more and more terrible for us to figure out how those pieces are going to go together here, right? So we're trying to improve the goodness of our estimate by increasing the degree of polynomial that we're using to estimate that one little piece of our function right there. Yeah, splining. So splining, a cubic spline is a very typical thing to do to fit a cubic function through some curvy function out there. We're splining. This is a quadratic spline right here. Exactly. Good words right there. Awesome, people in chat. Thank you. So let's do the fun part and actually derive this formula here. We're gonna derive the formula for the general area underneath a general piece of a quadratic, right? So we need to draw ourselves a good picture for this guy right here. So, and I'm gonna do some smart things for myself. Before I start setting this up, we want to remember sort of the lessons that we learned from our physics sections. When we're doing something super general, we get to pick all of our like locationing, right? We get to pick where our axes are, what values of interest we want to use. What I know is I need to be able to pick 3 x values here to just do a general example of this, which we will then generalize to everything else. If I got to pick 3 numbers to do math with, if I get to be the picker, what are the 3 numbers that I'm going to do generic math with? I know what that list is. By far, the 3 easiest numbers on earth to do math with are 0, 1, and -1. Now, 1 and -1 are a little too specific because I don't want to pin down exactly what my delta x width is going to be, but I'm going to at least pick like 0, 1 step to the right of 0, and 1 step to the left of 0 as my x values of interest, just because I'm trying to do myself a favor here, right? This is just like, help yourself out, right? So I'm going to draw a sort of left-right symmetric graph right here. And I'm going to imagine for myself maybe that we've got sort of like, maybe here's like our 3 heights on our graph of interest, right? This right here is at x equals 0. I'm going to go ahead and call this location right here x equals h. So h is sort of like our delta x here. And therefore, this is going to be located at -h. And what we can all kind of picture here, oh man, I did the dumb thing and I drew my points before my parabola, is that there should be some parabola that's going through here. But notice that even though that parabola goes on forever, We're really just interested in the area that is between the 3 points, right? By the time we're getting to this area that's to the right of my dashed line, that will be part of our next Riemann object that we're adding up. That will be between the next three x values that are out there, all right? So what I want to find right here is I know this parabola has the form and I'll just say this is just y equals ax squared plus bx plus c. I have no idea what this equation is. It's just a general form of a quadratic. And what I'm interested in this case is the area between negative h and positive h right here. So now I'm just sort of making up words right here. One Simpson-Riemann object, right? The one little area estimate piece that we're accumulating right here should be the integral from negative h to h of ax squared plus bx plus c. So what we don't know though is what is a and what's b and what's c in this case, but we're going to get a little bit of help for that. So we're going to do this sort of in two pieces. First, let's do the integral and see what the most generic form is of our area, and then we want to rewrite the area because again, having this in terms of a, b, and c doesn't help me because what I don't want to have to do is literally come up with what parabola this is. What I just want to use are just the heights that are associated with this thing here, right? So I'm thinking that this point is at, for example, negative h, f, or okay, I'm not even going to call that f right there. Let's, okay, thank goodness. And let's just call this here y0. This should be at the location 0, y1, and this is at the location h, y2. All right, so I'm just calling my three y values here, y0, y1, and y2. I know that this has an x value of negative h. I know this has an x value of 0. I know this has an x value of positive h right there. So just to give some generic names to those points of interest. Because again, what we don't want to have to do is literally come up with a formula of a parabola for all of our breakdowns. We just want to use the x and y values associated with the actual function of interest. So let's do the integral here. We should be getting 1/3 ax cubed plus 1/2 bx squared plus cx. It's okay that I'm using c here because I'm doing a definite integral, so I'm not getting any, not getting like a plus c on the end. This is my x is equal to negative h, and my x is equal to positive h. So it looks like I'm going to be getting here my first grouping, 1/3 a h cubed. Ooh, yeah, 1/3 a h cubed plus 1/2 b h squared plus ch minus. Now I'm plugging in negative h into this, and you should notice when we plug in negative h, negative cubed does give us negative. H cubed. Negative squared goes back to positive. Negative first order does give us a minus cx here. Okay, there's all my pieces. I got a little bumpy down there with my writing, but that's okay. So let's do this addition, and then we'll come back to see how this relates to the diagram that we drew. Notice here, 1/3 ah cubed, 1/3 ah cubed. That's the negative of a negative. So we're actually going to get here 2/3 ah cubed. You should notice here we have a positive 1/2 bh squared and a negative 1/2 bh squared because we're subtracting off another positive one. So those actually all canceled, interestingly. Finally, we have a positive ch and another, that should have been an h right there. Man, I wrote a bunch of those wrong. Positive ch and negative of a negative is another positive ch. So we're going to get a plus 2 ch. So what? Zinni, come on. Hey, Zinni, come on. Let's go. Get outside. Let's go. Let's go. Go outside. Outside. Go. How do you outside? My God. Normally they're already outside. Okay. So here we are. So we got this expression right here. Only thing I want to do is just a little bit of factoring. I don't like fractions. There's h's in both these things right here. So I'm going to go ahead and factor out an h over 3. And this is going to leave me with a 2ah squared plus 6c. So I'm claiming that this is the area under one Simpson-Riemann object, right? Where it's got like a rectangular base, but a parabola top. That will be the area of it. And I did the integral to find that. Now, the thing that sucks about this is that this is in terms of, so h is good because h is the same thing as delta x here, right? But this is bad because I don't want to have to find the actual parabola every time, right? It might have, I am showing no dropped frame, so if you want to refresh, that might be your move there. So what we want to now do is decide what we do know, right? Well, again, let's say again what we don't know and what we do know. What we don't know is the equation of the parabola for every single Simpson-Riemann object. What we do know is the individual heights and x values of all of our objects. So what I want to do is I want to rephrase this AC expression in terms of y0, y1, and y2. All right? So let me just say that down here. We want to rephrase y0, y1, y2, right? That's what we want to do. We want to get back in terms of our heights, our function values, right? That's the stuff we're actually going to know. The ABC will be a ton of work for us to get every time. So here's what I'm seeing. Oh, what was that move? Seriously? Oh my gosh. Area. Oh my gosh. What's happening here? Oh my gosh. All right, I'm going to have a little computer fight here. All right, so what we have when we're doing Riemann sums is we have access to the x values and the y values. We don't want to actually literally find the parabola itself. So I just want to rewrite our answer down here in terms of the known heights that we'll be able to actually extract from the function or from the table, right? So let me do myself a favor here and do that. So what I'm going to do here is I'm going to use our ideas up here, right? I've got what my function is going to look like here, right? So we've got that. So we've got our x0 stuff, our x1 and our x2. This is negative h. This is 0. This is h. We've got f of x0 then should be f of negative h. And this will give me ah squared minus bh plus c, right? I just plugged in negative h into our generic formula. You should notice that when we do f of x1, this one's really nice and easy. This is just f of 0, and so that's just what c is. And by the way, this is what we're calling y0 here. This is what we're calling y1. And finally, we can do f of x2 here. That should be f of positive h, and that's just going to be ah squared plus bh plus c. So my goal is to come up with a statement that looks like this stuff in the parentheses, and the way that I want to do it is by using my pieces y0, y1, and y2 right here, right? This is sort of my like stuff of interest that I want to use to make this stuff that's right here. Right? So here's the things I'm seeing. I don't directly know what to do here, but here's the thing I'm seeing. There's no B parts in here, and I'm actually noticing there's a positive BH and a negative BH here. So those look like they could maybe like cancel nicely to give me the stuff I want there. The other thing I'm noticing here is 2AH squared. Well, I'm also noticing that there's h squared here and h squared here. So my inclination right away here is what happens if we just add together these statements here, y0 plus y2. I'm noticing here that y0 plus y2 is going to give me 2ah squared plus 2c. All right? I've added them together. I got two AH squareds. The BH is canceled, and I got two C's. I didn't talk about Y1 at all yet, right? This is really close to what I want. All we're missing is four C's. Well, guess what? C is really easily described in terms of Y1. That looks like four Y1s are what we actually need. So, hey, I nailed it. Got this right on one piece of paper here. So it looks like we're going to get a Y0 plus four Y1s plus a Y2 is going to give us our 2AH squared plus 6C, just like we wanted. And now we can finally rephrase this as saying H over 3 times 2AH squared plus 6C, we can instead rewrite as H over 3 times Y0 plus 4Y1 plus Y2. So this is the general structure of all of the areas that we are going to add up in all of our Simpson-Riemann objects. If you know the H, which is delta x for us, then we can do H over 3 times the height of the first x value plus 4 times the height of the second x value plus 1 times the height of the third x value, and that will exactly give you the result of this integral computation, right? So here's where I said, it's not like we want to go do an integral for literally every one of our blocks out there. That would be a giant pain in the ass. What we just did is we did one very generic case of this right here to recognize that all of our parts are going to look like this part right here. All right? So let's kind of generalize what we just said right here. So now I think we can say, should be giving us something like H over 3 times Y1 plus, or sorry, Y0 plus 4Y1 plus Y2 plus H over 3 Y2 plus 4Y3 plus Y4, right? We're going to get these same generic things because all that's happening here for these next terms, we're just doing like a horizontal shift. That should have zero impact on the integral that we did. Shifting a function left or right does not change the area underneath its curve. So that's why I know this is acceptable for me to just slide my x values down and use the same structure out there, right? So hopefully you can kind of see where we're going with this guy then. Let me keep sliding this out right here so I can actually write my final statement for this guy. And what we're going to see then is it looks like we're going to be able to factor out all of these h sub 3's. And again, this is our estimate for Simpson's rule. Area estimate, not our true area, is going to be y0 plus 4y1. Now notice, there's going to be y2 as a single as the upper bound, and then a single y2 as the lower bound. So we're going to get two y2's. Looks like we're going to get four y3's. Looks like, again, this y4 here is going to be buddied up with the first y4 that's over here. And so we're going to get this pattern. How did I write my pattern before here? Of 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1 is going to be the pattern of coefficients on each of our heights associated with this to get our Simpson's rule computation that we're looking at right here. And so in general then, we will say our Simpson's estimate for the area from A to B under f of x. Where this came from was us actually computing integrals of parabolas, but it turned out to be nice and like linearly representable again out here like we kind of really want it to be. So now we're back in the land of we're just doing a bunch of multiplication and addition, and we've got actually a very accurate estimate for our integral here. And so I've got this notated here as just, so notice here, this doesn't lend itself as nicely to stating a summation because we have all these, like these constantly changing boundaries on, or coefficients on these guys here. So this generally doesn't typically get listed like as a, in summation notation, but I am going to tell you that there is actually a super convenient shorthand associated with this one that's not obvious. But like one of the problems of the book just asks you to show that it's true. So 1, 2, 4, 4, 2, 4, 2, 4y3s, 2y4s, and I've got this written here as dot, 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 2 yn minus 2, it's a y, plus 4 yn minus 1 plus y sub n. That's our wrapping up right there. It's always ones on the outside, and then fours, and then twos, and then fours. And again, notice the way that I'm doing that with my fingers, there has to be an even number of these things. We have to have an even breakdown for n, or else we can't kind of set up our Simpsons rule stuff right here. So this is our general Simpsons rule formula right here. And it turns out, so this is our, so here's what I should be doing notationally. That should be an approximately equal to. This is our S sub n. And I'm not like assigning this problem right here or anything, but the book does point out that in exercise like 48 or something, they have you show that S sub 2n is actually the same thing as 1/3 of the trapezoid rule for n plus 2/3 of the midpoint rule for n right there. So this is actually another way of saying Simpson's rule is actually exactly equal to a weighted average of two of our other rules. Just like trapezoid rule is the average of the left hand and right hand rule, Simpson's rule is a weighted average of the trapezoid rule and the midpoint rule. To show that's really just a bunch of algebra to see that you're going to get the same pieces that are out there. You can see that it's a weighted average, 1/3 of one plus 2/3 of the other out there. But that's kind of a convenient relationship that exists between all these guys right here. So there's our Simpsons rule. And I do like the derivation of this because this summation feels to me like the other ones did, just with some slightly more exciting coefficients. And it turns out that you do have to know some calculus to do this one, right? I could teach a non-calculus student each of the previous four systems, but you have to be able to understand the integral here to get our general area right there. And then we're just rewriting our area in terms of x and y instead of coefficients on a quadratic, because I don't want to find the quadratic. I just want to use 3 points. So this system now allows us to just use 3 points of information and output the area underneath the parabola of interest right there. So we did just a little bit of eyeballing right here to see how can we rewrite this stuff inside the parentheses in terms of y0, y1, y2. We added a little bit of stuff and saw that we were really close and that the remaining parts that we needed were really easy to add in here because y1 is exactly what c is, and we just needed 4 copies of c. So we just added 4 copies of y1 into the mix, and we had exactly the components in a and c rewritten in terms of y0, y1, y2. And so that gave us our one piece, and then we can just add up all of our adjacent pieces to each other to get our full sum that's out there. So I really like the derivation for this. I feel like this is like a cool thing that we can build up this formula for this. And again, I really like these ideas of where we want to do calculus and we can't. So we're going to have to approximate. To get a good approximation, we're going to have to do calculus, but we don't want to do too much. And so we want to come up with a way to reduce our calculus that we're doing to avoid doing calculus down to just an algebra problem here. So we avoided doing calculus once, and now we're sort of avoiding doing calculus in a second layer by having rewritten this sum as just a bunch of multiplications and additions going on out there. So this feels satisfying to me out there to kind of be able to turn calculus problems into non-calculus problems by just doing the calculus once ever. And now we have just an algebra rule to represent a calculus concept, and that's pretty neat. And again, also cool that a lot of these approximations are deeply related to each other right there with some very simple relationships like this one here. So those are the 5 approximations that we want to be able to use here. And again, like these are pretty easy to use. You just compute the x values of interest, use the x values to get the y values of interest, plug them in, and you got an answer right there, where h is the same thing as delta x, remember, right here. I should write this in here. H was our width right there. So what we now need to talk about is our error bounds. If we're making approximations, we need to know how good those approximations are. So let me just bump all these guys down here a little bit. And so what I'll tell you is this. Coming up with the boundaries for the error, being able to say, I know that my error with this approximation will never be greater than blank. is a little complicated. It's surprisingly less complicated than you think, but it's never anything that anybody ever really talks about. So grad school, or maybe if you're taking like a 400 level numerical analysis class, I guess it might come up in there too. But it's pretty typical that people take numerical analysis first in grad school, but it's not really uncommon to do it like I said, a 400 level class or something like that. And if you take and by the way, numerical analysis is saying all the problems in math that we can't directly compute, we want to have a computer compute them for us. And that's like the whole theme of this whole section, right? It's like, how can I add up like a billion numbers to represent doing this one integral? Well, numerical analysis is doing the numerical integration instead, and other things aside from integration, techniques for doing stuff that you can't do perfectly exactly. So numerical analysis covers a lot of that stuff. In that class, it's very likely that you're going to derive exactly the formulas that you're about to see in 1 second here. And you should do this. Aside from the fact that all of you are going to grad school, because why wouldn't you? Do take numerical analysis in grad school. It's super interesting. It's a very satisfying relationship between mathematics purely and computer programming applicably. Because like we've said, I mean, if basically no functions are integrable, then that means that you have to use numerical methods to integrate anything that's actually of interest. So taking numerical methods class is going to be important for you to be able to say, no, listen, I know I can just do this sum instead of that integral, and I know that my answer will be accurate to within our desired accuracy anyway, so we'll just do the sum instead. That's the kind of things that we want to be able to be confident about with our numerical analysis statements. So you should do that. I was very sad that just the classes that I was taking, I remember there being an overlap in my schedule, and like all my friends were taking numerical analysis, but I was taking a probability and statistics class instead that they weren't taking, which I'm very happy about. But like every time they told me what they were doing, I was like, well, that sounds so cool. I wish I was doing that too. And I wasn't, and it made me sad. So take a numerical analysis class. It's really cool. It shows you how to numerically compute things when things get too tough for us to do our like intended calculus methods or our intended linear algebra methods, stuff like that. So the bottom line here is this really is at least a 400 level, if not a graduate level topic right here of coming up with the formulas associated with our boundaries on our errors. So very appropriately, the book just says, here's the formula for bounding the error to make sure that we know what the most amount of error we could ever see if we use this given approximation. So what I'm going to do is I'm just going to show you the three errors right here, and then we'll talk about them a little bit and do a little bit of examples with kind of making the claims that we want to make with these. So what we've got is these error bounds for the midpoint, the trap. Oh wait, oh my gosh, I'm forgetting the most exciting thing that we want to do right here. Let's stop and actually look at these things. I want to see these errors right here. All right, so what I did is I wrote some code last night so that we can actually have a computer do this, because this sucks to do by hand. You're going to experience that, and you're going to be encouraged to learn to program so that you don't have to do that again. So let's pop on over to the browser over here and see what we're going to see. So I wrote a little bit of code to do this for us in Python here. Just move this a little bit so it stops bothering me here. There we go. And so a couple small things. This code is written in Python. It really wasn't too hard for me to do. Again, it's just a lot of addition, subtraction, multiplication, stuff like that. If you would like to download and install Python, what I would recommend that you do is download the Anaconda installation of Python. Python is just a programming language, but what you're going to want is not just the language, but also software to write it in, right? So this is like saying just because you can write in English doesn't mean you already have Microsoft Word. Microsoft Word is the program that allows you to write your English paper in the language English there, right? So if you want this, then you can just Google like Python Anaconda download. It's kind of a big download, by the way. It's going to be like a gig. It's kind of big, but if you want to do this, then do this, and you can follow along in my notebook. If you do this, it's going to take you to like a main page. You're going to click download. It's going to zoom you to the bottom down here, and you're going to see there's your Windows, there's your Mac, there's your Linux. Oh, nice. I finally got rid of the 2-point stuff right here. Most all of us are on 64-bit computers right here, so you should download this top one for Windows, Mac, Linux, stuff like that. Like I said, it's like a little bit over 1 gigabyte. It's a pretty big download, but it will come with not only Con, yeah, I'm gonna at least post this notebook. By the way, speaking of which, I don't have a GitHub set up because I'm stupid. I need to do that like sooner rather than later because I do need to share more code things. But I'm gonna give this brief explanation and just like a downloadable file that has my code in it in Canvas at least, and so that will be directly linked there. But you are correct. I need to share this in a smart way here. So in any event, here's where you can download this stuff, download and install. Once you have the Anaconda install of Python, which is like a broader package right there. Ooh, yeah. So, Coffee Gopher, Python 2, as of January 1st of this year, is no longer supported. Like they're not planning on doing any more updates for it. So, lots of stuff that you'll find is in the slightly older version. But now companies are finally like sort of being forced to like finally actually migrate over to Python 3. I learned to code in Python, and I kind of, when I was starting like 4 or 5 years ago, it was right at the time where it was like, should you use 2 or 3? Well, most major companies still use 2, but you should definitely go to 3 for the future. And so I used 3. So this is a thing where the differences are relatively minor in the broad scheme of things. But like if you're a Fortune 500 company that has a billion lines of code, it's a giant pain in their ass to transition all those little tiny things into Python 3, and they have to do that now. So they don't have to do that. They can, well, whatever. Anyway, used to be Python 2, and just as of this year, it is finally sort of out as of January 1st of this year. So it's all, so that's what I said ooh about when I look down here, is that I expected to see like the Python 2, Python 3, but they're only giving us the option for Python 3 here. You have to go to a special place to get the old school Python 2, which we won't ever use. So download this. It will give you a thing called the Anaconda Navigator. Once you open up Anaconda Navigator, you will see in there a Jupyter Lab. That's if you can barely read my heading up here. It says Jupyter Lab. Jupyter Lab and Jupyter Notebook give you this cell style way of writing code. So I'm going to talk through this stuff. Um, yeah, so you're right, the con. There, I am talking about a very bulky download here. There are lighter ways. I just typically point people toward the Anaconda version just because it is a guaranteed like one download and never anything else. But I think you can do like the mini Conda or something like that. And you're totally correct that 3.9 also did just recently come out, and I'm seeing 3.8 right there. But that's all technicalities for developers that aren't going to affect us here. So let me just briefly talk through some of the stuff that I'm going to do right here. I feel weird about showing code that I don't describe. And again, you guys are mathematical adults that basically have to learn to code because you're smart. Smart people are going to write code in the future. It's 2020. You're going to write code for your job if you are in any sort of STEM-based job. So start getting used to that idea. I wish somebody would have just punched me and told me that when I was 19 and I did not know that, and I wish I was programming this whole time. So I'm going to just talk through every line of code here really briefly. This isn't something where you need to understand everything, but you should be able to generally follow what I'm doing here. First things first, I'm going to want to use some libraries that have some specialty functionality. NumPy stands for numerical Python. Pandas, I forget. There's some smart acronym for pandas out there that I don't remember what it is, but this is going to allow me to organize my information sort of in like a more advanced version of an Excel spreadsheet. I'm going to define a function for us here that's going to be called getApproximations, and it's going to take in the number of subdivisions of interest. Inside of my function that I'm defining to get all the approximations, I'm going to define the curve of interest, right? So here like 1 over x. So this is saying we want to approximate the integral of 1 over x. I'm going to establish some parameters here. So my lower bound of the integration is 1. The upper bound of my integration is 2. So this is saying we're really looking at the integral from 1 to 2 of 1 over x. That's what we're trying to approximate here. I'm going to state what my delta x is there, b minus a divided by n. I'm just identifying some variables of interest here. And now what I want to do is get the x values that I want to use for each of my approximations. So in Python, anytime that we use brackets, that's going to be defining a list of values. So what I want my list to look like, you should recognize that little chunk right there. That's a plus some number of delta x's. Which number of delta x's? Well, I want it to go from 0 to n minus 1, and that's what that will give me right there for all those I values. So x left is going to give me a plus dx, a plus 2 dx, a plus 3 dx, blah, 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 a times n, a plus n minus 1 dx. Similarly, for our right-hand x values, my list is going to notice that here I'm constructing this the same way. And in fact, this is just like our summation notation right here. In this case, I've left the sum the same, but I've changed my bounds for my sum. Now, instead of going from 0 to n minus 1, I'm going to go from 1 to n. Tiny little technicality here. Python, when it does ranges, includes the bottom, but does not include the top. So it's like a bracket parenthesis every time it does a list here. So this one includes 1, but it only goes up to n. So here I'm going to get the upper chunk, so A is discluded. And for our midpoint rule, I'm going to take the average value from the left chunk and the right chunk lists. So this is saying grab the ith object from the left list, and then also grab the ith object from the right list and average them. That will get me all of my midpoint x locations. So these are my three x lists for x left, x right, and x mid. I'm going to use those to get my my y values. So these are each of my individual y values here. Excuse me. This list is each of my y values right here. I'm going to add up my y values with a sum, and I'm going to multiply it by the width that we have factored out. So I'm just exactly following the formulas that we built here. Again, this is a bracketed list that I have highlighted, and this is going to say compute f of x. And notice we defined f of x to be the 1 over x function. Compute f of x for each of the x values in the left list. Compute f of x for each of the x values in the right list. Compute f of x for each of the x values in the mid list right here. We sum all the y values, and then we multiply the sum of the y values by the width that we've factored out. What we also saw earlier was that our trapezoid approximation was just the average of our left and our right hand approximations is what we've got right there. And I guess actually I didn't include the Simpsons rule, but we're going to see some nice stuff in here. And maybe what my activity should almost, maybe I should just do like for extra credit, buff out my stuff so that there's Simpsons rule with everything in here. Maybe that's a thing. If anybody wants to do that, do that. I will give you gold stars and bonus points for that. So what I'm going to do here is do two different things. One, I'm gonna comment out my return statement and just leave in a print statement here. And so what this is going to do now is I can say, give me my approximations for the integral from 1 to 2 of 1 over x in terms of the left sum, the right sum, the midpoint sum, and the trapezoid sum. As you can see in the red writing right here, it's going to round my left approximation to 6 places, round my right approximation to 6 places, round the midpoint to 6, and round the trapezoid to 6. And I could, so I'm going to run this cell. Oh wait, I don't think I ran this guy here. I'm going to import my libraries, which I haven't used yet. I'm going to define my function. Then I'm going to use the function. I created a function called getApproximations. Now I'm going to make a call to the getApproximations function, and I want to use 5 subintervals. And it's going to give me these approximations here. We can see, by the way, notice that I'm getting 0.74, I'm getting a 0.64, and then both the midpoint and the trapezoid approximations are about halfway in between these two guys right here. And in fact, trapezoid approximation is exactly halfway in between these two. The reason that this is unsatisfying to me as an output is because I want like labels and stuff right like that, right? I kind of want to build like a table for like how many n we have, how many subdivisions, and what our approximation looks like. So here I'm going to buff it out a little bit more. Now I'm going to say, listen, let's instead first print just a header. So this just prints the text header right here. It's just, there's no computation happening there. And then I'm going to create a for loop here that's going to say, listen, for each of the number of subdivisions n in the range from 5 to 51, counting by 5s, this is really from 5 to 50 since Python discludes upper bounds. So this is going to say, notice all of our n's right here go from 5 to 50, and it's going to give us our left sum, our right sum, our midpoint sum, and our trapezoid sum. And you should see the satisfying thing that's happening is they all seem to be sort of like converging on some value of like 0.69 something. Notice that the actual value of integral from 1 to 2 of 1 over x is the natural log of 2 minus the natural log of 1, which is really just the natural log of 2, right? Natural log of 1 is 0. So our true answer that we're sort of comparing against here is this guy, right? It's the natural log of 2. Python, as a general programming library, does not have math functions like natural log in it, but the numerical Python library does have all the math functions that we want. So I'm saying here, hey, numerical Python library, do me this favor, compute the log of 2 for me. And also you should satisfyingly know, according to any science person, there is only one log, the true log, the natural log. If I wanted to do a log in another base, I would have to use a more specific function. The generic log function in like every programming language ever by default does natural log because any STEM person knows that that's the log that you use for literally everything out there. So this is going to do the log base e of 2. And the np dot in front says I am asking the specific library, the NumPy library, to do this computation for me because general Python doesn't otherwise know about computing logs. So I'm asking a specialty library to handle that for me. But again, this is slightly unsatisfying to me because what I also want to do is think about what the errors look like in association with each of these guys. So this is a little bit of me doing something more fancier than is directly necessary. So, but I still want to show you kind of what I'm doing right here. What I'm going to do is I'm going to put these into, rather than just like literally a printed set of columns where like I literally am using tabs to get my spacing between these things. I want to do this in more closer to like an Excel spreadsheet rather than just like literally me writing things that are vaguely organized in something that looks like a table. I can tell you that I set this up before and had a bunch of like garbage looking stuff. I want this like auto formatted for me. So what I'm going to do is I'm going to use the pandas library to create a data frame, which again, data frames are not natively known to Python, but pandas as a specialty library handles stuff like creating these Excel-like data frames. So I'm going to say, listen, let's make a data frame. I'm going to name my data frame approx because it's going to hold all of my approximations. The column titles in my data frame are going to be the number of subdivisions and the 4 out of 5 approximations that are considered in this case. And what I want to do to build out this data frame, right? This line of code will just give me an empty data frame that just has 5 column names and nothing in it, no content in it. What I'm going to do then is I'm going to loop over all of my different ends of interest, right? Just this column of ends from 5 to 50. I'm going to say, listen, for all the ends counting by 5s from 5 to 50, let's do the get approximations function. That's going to spit us out just this one row of stuff right here. And what I want to do is basically say like, add this row to Excel, then add this row to Excel, then add this row to Excel. And by the way, I'm glad I scrolled up right here because I want to remember that I want to go back to actually returning instead of just displaying the results of the computation here. That's a little bit of a technical thing. Don't worry about that. But I'm saying let's get the one row. Get approximations is going to create one row based on one n value, and I'll save that as the variable a. What I then want to do is say, hey, listen, to the approx data frame, go ahead and append, stick on to the data frame, and I need to tell it which column each of the terms belong in. So for the n column, put our current value of n is known by the for loop. For the left column, put in the object at index 1. Python index is base 0, so 0 is the first object, 1 is the second object, but that's going to be the object in left. 2 is the third object, that's at right. 3 is the third object, mid. 4 is the fourth one at trap. And then apparently I need to do an ignore index statement there. I don't even remember why that was true, but I got yelled at and I added it in there and it worked fine. So now when I run this, it's going to build the data frame and then I can show the data frame right here. So this is maybe a slightly more satisfying organization of the results that we got right here. It does this like general light shading. You can see that just by hovering, it will like do some like light highlighting and that's very satisfying. But one of the last things that we really wanted in here was what are the errors associated with each of these guys? So what I'm going to do is I'm going to compute the error. I know that our answer that we should have been getting for everything was log 2. So all of our answers are being compared to natural log of 2. So what I'm going to do to get our errors here is I'm going to add a new column. I'm going to say in the approx data frame, my new column of our errors associated with our left sum should be the natural log of 2 minus every single one of the values in that column. So the one thing that's really nice here is that I'm doing a constant minus a whole column of values. But both NumPy and Pandas as libraries are very smart about thinking about how to like do that as really meaning like a whole column of the natural log of 2 minus a whole column of our left-hand approximations to get a whole column of our errors out there. And so it's smart about doing like, because this really is just a constant minus a column. And that's a little weird in a sense, but these libraries smartly handle that stuff under the hood for us. So basically these 4 statements here are going to add 4 new columns into my data frame over here. So I can now look and see how far off are all of these estimates from all of my true values. They'll give me my errors here. So here's the thing I want us to be able to see out of this table. This is kind of just a bunch of numbers, but here's some important things. Important thing number 1, once we have the most number of subintervals that we ever did, we did 50 subintervals as our largest number of breakdowns. You should be seeing here that we have our left-hand sum error 0.005, right sum error also about 0.005, but our midpoint and trapezoid rules 0.00001, 0.00001, right? So this guy has like 1/50th the error at this point. Both of these have about this is about 1/50th the error, this is about 1/25th the error of our left and right hand sums. So one thing we can see is when we go out to a large-ish number of subdivisions, midpoint and trapezoid rule are totally crushing the left and right hand rules, and the Simpsons rule will do even better than that. The other thing I want us to see here is that it looks like when we do the left-hand sums right here, look at these two numbers. We go from about a 52 here to about a 26 here. It looked like in our first step here, going from 5 to 10 subdivisions, we reduced our error by about half. Same thing here, for about 48 to about 24, reduced our error by about half. In our midpoint, we went from about a 12 to about a 3. We cut it down to only about a quarter of our error by doubling our number of subdivisions. Yeah, it does make sense that the midpoint is going to be one of our best ones right there. I agree with that. If we, yeah, looking at our kind of diagramming out there. And again, our trapezoid one is going from about a 24 to about a 0.06. So what we can see here is that the left and right sums, when we double our n, we're about halving our error. Our midpoint and trapezoid, when we double our n, we're about taking only a quarter of the error, which is way better, a fourth as much error out there. Simpson's rule, because it is a quadratic approximation, will do even better than that. So this is a nice thing to see with our error estimates of watching the error get really, really small right here. And hopefully you're pretty happy with this. I mean, the midpoint rule having an error of only about 1 in 10,000 by doing 50 subintervals, it's pretty good, depending on our purposes out here, right? I think this is nice to like just kind of, this is just a big, in one sense, just a big old table of numbers, but I do think it's convenient to see like, yes, everything is converging on one value. The value it's converging on is what we know the true value to be, the natural log of 2 out there, and we can see that our errors get smaller at different rates. Halving of errors by doubling n, quartering of errors by doubling n, and that doesn't always follow exactly true right there, but that's a vague approximation. So let's go look at our error boundary stuff here and do 2 computations and call it a day here. So popping back out of my Python stuff here, let's head back over to Word. So here's our error bounding rules for the midpoint rule. Suppose that the absolute value of the second derivative of the function of interest could be bounded by some k. Wow, this is a horrible start already. I have no idea what's going on here. For all of the x values in our interval of interest, right? We're doing an integral from a to b, so this has to be true for all the x values. Then with the error stated as e sub m, the error of the midpoint rule, then we can say that our error is guaranteed to be less than whatever the heck we're going to get right here. You should notice that as n gets larger and larger and larger, this number gets smaller and smaller and smaller. And so we're going to get a better and better bound for our error, a narrower window in which we're going to be able to see our answers. And that's good for us. We want to be minimizing error here. All these statements, I'm going to just get them all on screen once, look basically exactly the same, right? They all have a statement about bounding the second derivative with some constant k. Here, the Simpsons rule bounds by the fourth derivative, but that's because these were first order approximations. These are second order approximations, which is part of the reason for that. And again, learn about this in grad school, why we have fourth order instead of a second order derivative right there, graduate topic. But again, if we can find some number that's bigger than all of the outputs that we get from the fourth derivative of this function, then we can use that constant here. And notice we get some wilder terms here. This has a b minus a cubed over 24n squared, b minus a cubed over 12n squared, b minus a to the fifth over 180 n to the fourth. And it's like, where in the hell do these numbers come from? Go to grad school. So let's take a look and see how to use these formulas here. In particular, I think the weirdest thing is you should be saying, what the hell's k? And we need to work to find it. So let's look at an example here. And notice kind of our takeaway here by vaguely looking at these is this. In all 3 cases of the bounds of interest here, these bounding formulas, these bounding theorems, the parameters of interest are the error, whatever this k boundary is up here, b and a, and the number of subdivisions n. We're always going to know a and b because we're always going to be doing a definite integral from a to b. Therefore, if we know any 2 of the remaining 3, we can solve this inequality for the third and know that piece of information. Furthermore, you should notice that k is actually up in the hypothesis of our theorem up there. This is saying we sort of need to know k to get off the ground here. So really that means we're also going to know k. We have to work to find k, but k is something we have to know here. So that really makes this boil down to just the knowing either e or knowing n. We have to know one to get the other. If we can identify k, and the desired error is known, then we should be able to solve for n the number of subdivisions that we need to fall within that amount of error. The other thing we could do is if we can identify k, and if we know how many subdivisions we're gonna do, we can get a guaranteed bound on the maximum amount of error that our approximation will divide. So basically we're saying a and b are given, k we have to work to find, and you can either know the error that you want and solve for the number of subintervals, or know the number of subintervals you want and solve for the amount of error you're going to get. Those are the two ways to like use these formulas here. All three of them are generally structured and generally have the same hypotheses, the same right there. So let's just do one example of each of these problems here, and we will call it a day. Importantly, I'm going to go back to our buddy, e to the x squared right there. It's the thing that we literally couldn't do. You can't do this integral, and literally nobody on earth can either. So coming up with estimates for the value of this integral is necessary in life because it's literally not doable directly. So, and I forgot to make an important statement here. Let's do the hardest possible case here since I'm doing an example. Let's do the Simpsons rule case right here. Let's estimate the value of the integral from 0 to 2 of e to the x squared using Simpsons rule. So here's the things I'm thinking. One, if I'm going to do this by hand, I would never do anything by hand with more than 10 subdivisions. So maybe I want to know, like, what's the best error? What's the most error I'm going to come up with on my answer here if we do use 10 subdivisions here? How good of an answer am I going to get by hand if that's how much work I'm willing to do by hand? Our second question, I flip it around. I'm going to say, all right, I actually need to get a maximum error of 0.00001. How many subdivisions would I have to break this thing down into to have a guarantee of no more error in our answer than that? So these are inverse questions of each other right here. In one case, we know n and we want e. In the second case, we know e and we want n. What we have to know for both is what's k? And so we need to work on that here. So let's see. So here's the thing that I know about Simpson's rule. So I'm going to leave those two questions, I guess, right there. For both, we need to find k. To find k, we need to know f to the power of 4. I hate when it gets rid of my parentheses right there. We unfortunately are going to need the fourth derivative of this function to be able to find a y value that is the maximum possible y value that we'll experience on our interval from 0 to 2. So first things first, let's go ahead and find the fourth derivative. So the first thing that I'm going to do here is say, all right, f of x is e to the x squared. Therefore, f prime of x, doing a little bit of chain rule here, should be the derivative of the outside function is just e to the x squared. The derivative of the inside function is 2x. So I'm going to get a 2x e to the x squared. Here's my first derivative. I need my fourth derivative. The second derivative of x right here, we now have a product rule, and there's going to be a chain rule in this part here. If I take the derivative of the first piece, 2x, I'm going to get 2. When I take the derivative of my second piece, e to the x squared, I'm going to get a 2x e to the x squared, and that's going to give me 4x e to the x squared. Right. Wait a minute, did I... Messed up my product rule there. Back up, that never happened. You never saw that. Okay, trying this again. Derivative of my first piece, and the derivative of my... All right, so derivative of 2x is 2. We leave the other parts alone. Plus, leave the first part alone, times the derivative of the second piece. This should be giving me 2e to the x squared plus, notice 2x times 2x is 4x squared e to the x squared. So that's my second derivative. We still need to take 2 more. The third derivative of x here, now I'm using this stuff over here. So that's my first part. And then over here I'm noticing I have a product rule. So first the derivative of 2e to the x squared. Well, 2 is just a constant, so that doesn't affect anything. So I should be getting here 2 times 2x e to the x squared. So that's going to be 4x e to the x squared. Plus, now I'm doing a product rule here. So a derivative of 4x squared is 8x times e to the x squared plus Leave 4x squared alone. Take the derivative of e to the x squared, which is times 2x e to the x squared. And it looks like we're going to get an answer here of, I've got 4x of them, and I've got 8x of them for a total of 12x e to the x squared. And then here it looks like I have 8x cubed e to the x squared. All right, one more derivative and we've got the information that we need here. Now I've got a product rule here, and I've got a product rule here. So derivative of 12x is 12. Times the other part left alone, e to the x squared, plus 12x gets left alone, times the derivative of e to the x squared, which is 2x e to the x squared. That's my first product rule, plus the derivative of 8x cubed is 24x squared times the other part left alone, plus 8x cubed times the derivative of e to the x squared, which is 2x e to the x squared. So let's just simplify this, and we've got the term that we need here. So it looks like this is my, so everything has an e to the x squared in it. You should notice that. Every single term has an e to the x squared. So I know that I'm certainly going to factor out an e to the x squared here. It looks like this is my only constant term is 12. I have no others that are just straight up constants. All the others have an x in them. So I'm going to get a 12 for that guy. Everything's positive. I know we're going to get addition x. Now I'm looking for all my groupings of just x. That's constant. That stuff is x squared right there. That's a 24x squared, so I'm not grabbing those parts. It looks like here I have x squared stuff, and it looks like there I have x to the fourth stuff. Okay, I don't have any x stuff at all. It looks like next up is x squared stuff. So here I see 24x squared. There's 24 more x squareds for 48x squared. And then finally, my last term over here, it looks like is 16x to the fourth. All right, so we've got our fourth derivative of this guy here. And so now what I want to do is I'm interested in finding, I want to know the smallest value I can find for k such that f to the fourth, or the fourth derivative of x is less than or equal to k for all x in the interval from 0 to 2. Now, I want to show you how I know the answer to this easily, and then I want to tell you to watch out for some other scenarios here. One thing that you should notice in this whole string of derivatives that we're taking out here is this. Any even power right here, you should notice that this fourth derivative, okay, I don't want to answer it this way. I'm going to answer this in a smarter way. Here's what I'm going to do, is I'm going to just show you how I can actually get this guy right here. Well, I want to know, right, so whatever this curve of this gross fourth derivative function looks like, we are looking for a value of k. That's like a height that is an upper bound on the whole dang thing, right? So if I knew that my function was a purely increasing function, then I would know that just the endpoint is the highest value that we're going to get to. But if we don't always just have an increasing function, it's not, I don't know that I can necessarily say that, right? So what I'm going to do to make sure that I can actually be guaranteed within there is I'm going to just go to Desmos and look. And I'm going to type in this gross function. I'm going to start graphing. And our function of interest here is e to the x squared times I'm just looking for my parts here, so I'm not writing all this back over there. We got 12 plus 48x squared plus 16x to the fourth. So here's what I can see. Oh, where do we even go? So here's what I can see. Here's the important thing for me to see here. What I'm going to do is I'm going to smash this way down by increasing the y bound by like a lot. Right? Look at how huge these values get out here. But the thing that I want to see of interest to me is that between 0 and 2, this function is strictly increasing, right? So hopefully what you guys agree with is this. Whatever we get for f of 2 is the upper bound, right? Whatever that 25,000 number is up there, that's basically what k is going to be for us, right? Because that is the value of k that is above all outputs between 0 and 2. Since we're looking for the integral from 0 to 2, we need to know that the fourth derivative of our function is bounded by some number k, and it looks like the smallest upper bound I could place on this is, because this is increasing, just the upper bound, what's going on at x equals 2. You should notice that if we were going to have a function that was more like a bell-shaped curve or something like that, and then went back down, we would really be interested in just whatever the maximum value is. So this is almost just like saying, find the maximum value of our fourth derivative over the interval of interest and use that maximum value as the value for k. It's the value that's bigger than the function the whole time or equal to the function for the whole time out there. So this is just my graphical justification of saying the fourth derivative evaluated at 2 is an acceptable choice for k, because that height will be greater than or equal to all the other heights that we experience between x equals 0 and x equals 2. Right? So I'm going to come back to Word now, and I'm going to say in Desmos, and again, you're going to want to use a graph for this. Look how crazy these functions might get if you're computing a fourth derivative out here, right? In Desmos, we see that f to the fourth of x is strictly increasing. Therefore, f to the fourth of 2 is our minimum possible upper bound. So here I'm now going to say choose k to be equal to the fourth derivative of f evaluated at 2. So we choose k to be equal to f to the fourth evaluated at 2, and that is going to give me e to the 2 squared times, what do we got here, 12 plus 48 times 2 squared plus 16 times 2 to the fourth. This is the value of k that we want to be using for this inequality right here. Okay, whatever, uppercase, lowercase k, e to the fourth. And what are we going to get in here? That's 4 times 48. That's 160, 170, 180. 160. So it's a 194, right? Oh, wait, no, 192. Plus 2 to the fourth is 16. 16 times 16 is 256. And when I add all these up, if I'm just referencing my notes right here, I was landing at, what did I get for this gross one right here? 460 e to the fourth. Yeah. Yeah, that seems right. So this is the number that I'm getting for the value that I want to use for this guy. So now we can come back and actually answer each of these two questions. So let me copy and paste these down below, and we'll actually answer the question. Notice that the big work here was finding k. Finding a reasonable k value meant we had to take derivatives, consider a graph, compute an upper bound for the derivative of the function over the interval of interest here. So the other thing I want to do is I want to copy and paste my Simpson's rule boundary for our error right there. So let me copy and paste this down below as well. Okay. So we've got the parts that we need to deal with this guy now. Do that also right there. So we're going to do two different things here. So if we use 10 subdivisions, what is the maximum possible error? Well, we just start throwing stuff into an inequality now. We are trying to put a bound on our error. Oops, that's not how you write an E. Error, based on the Simpsons rule, is going to be less than or equal to the k value that we just found, is that nice gross thing right there, That's going to be uh, 460 e to the fourth, b minus a, 2 minus 0 to the fifth, all divided by 180 times 10 to the fourth. If we go to compute this in our calculators, we should be finding, I'm just going to bust this guy out right here. I'm getting here, let's see, 460 e to the fourth times 2 to the fifth divided by 180 times 10 to the fourth. What I'm getting here is 0.4465. Now, one of the things immediately that you should be saying is, well, is that good or not? And the answer is, it's really tough for us to tell because I don't know if the solution that we should be getting for our integral is some like gigantic amounts of area or some small amounts of area, right? If the total area under the curve from 0 to 2 is like 1, then this is a massive amount of error. Then this is like 44% error right there, right? So I do think another thing that's worthwhile to do in these cases to like go to Wolfram Alpha and to get their estimate for it, and then do more of like a percent error instead of an absolute error, which is what we're getting right here. But at the end of the day, this at least tells us that if you're going to use 10 subdivisions from 0 to 2 for the Simpsons rule, your answer is guaranteed to be no further off than 0.4465, rounded right there, relative to the correct answer right there. So we've computed a bound on our error there. I think the more interesting thing and probably the more practical thing that's done out there is saying, listen, this is the maximum amount of tolerance, right? If you're like an engineer and you need to say, I'm only allowed to have this much tolerance in my computations, then you need to know how many subdivisions you need to break this thing down into to still land at within the desired error of interest here. But again, this is just some more algebra. Just the point here is that we are now able to state 0.00001 is the error of interest. We want that to be less than or equal to our 460 e to the fourth times our 2 to the fifth divided by 180, and this is just n to the fourth. That's the thing that we don't know right there. And so I am going to, and by the way, with these things right here, this inequality generally doesn't sort of do a lot for me right here in this case. So what I'm going to do is I'm just going to rewrite this sort of as, I'm going to multiply the 180 up to the other side. I'm going to divide by the 460 e to the fourth, 2 to the fifth, and that should be, our 1 over n to the fourth. So now I've just got to flip this and take the fourth root. And if we go to our calculators one last time, last one of the day here, e to the fourth times 32 up top. We're dividing by 0.000. I think I skipped a 0 in that writing down there. There should be 4 zeros. And then divide by 180. And then I take the power of 0.25. And it's telling me I'm getting out for n right here, 145.36. N, last thing of the day, n has to be a whole number. And so we always will round up for n. I don't care if you get 145.00001, 145 would give you more than the desired error then. So we have to round this up. And so here our answer is going to be 146 is the number of subdivisions that are required to get a Simpson's rule estimate within 0.00001 of the correct answer for the function integral from 0 to 2 of e to the x squared. So we can now analyze the error that's associated with these guys as well, determine what number of subdivisions do we need to get a specified error, or if we have a chosen number of subdivisions, knowing what's the maximum possible amount of error we could possibly see from our estimate right here. So a little bit of work for these, but I think that these error estimate problems are, to me, a little bit more interesting than actually coming up with the approximations themselves. The approximations themselves are just multiplication and addition all over the place, so not quite as cool there. So there we go. Hoofda. We did it here. We painstakingly solved for an appropriate K value here. We used the K value to answer the 2 questions of interest associated with our error bounds. And that's what I've got for you here. So, yeah, I think that this is, again, another heavy algebra section here. I will be happy next week. We're going to get into very much our more calculus sections here. Calculus is all about infinity, and that's specifically what section 7.8 is about. Section 8.1 is going to be arc length. How do you get the length of a curve instead of the length of a line? That's also going to lead us to some surface area computations as well. We're going to get probability in chapter 8, which I'm super excited about. A lot of super cool stuff coming up here as we move into the second half of this semester here. So I'm pretty happy about all these topics. So I'm going to, your test will be posted at noon on Wednesday. You will have 2 days to work on the test and submit it by noon on Friday. Yeah, and that's all we've got for this week is just this one video. So I know I got a little bit long here, but obviously a little bit of this stuff took a long time to write out. And hey, it's only one video for the week, so I'm going to just say get over it. And we're good. So do good on your test. Answer your My Open Math questions about this stuff here. There's no by hand homework this week because of the test, no weekly writing because of the test for week 7, and we'll resume a normal week here in week 8. Happy week 7, everybody. I will see you guys on Monday.